not going. So I'm just gonna try to minimize it as much as possible.
Perfect.
Okay.
That's fine for us as well.
Okay.
Okay, so thank you so much for joining us, everybody. I would like to introduce Jean-Pierre Delacroix and Federico Rossi, who are going to be talking to you about cooperative autonomous distributed robotic exploration, or CADRE. So I'm going to pass it over to them, and looking forward to a great presentation.
Yeah, thank you. Thank you for the introduction. Indeed, I'm JP. I'm the principal investigator of CADRE, and Federico is my colleague and also the multi-agent planning, scheduling, and execution lead. And we're going to talk to you about both CADRE, but also a little bit in a broader context, some of the technologies around CADRE that have led to us bringing this technology to the moon, because we didn't, just wake up yesterday and decide to go to the moon. It's actually been quite of a process or journey to get from kind of the initial ideas of what we were doing all the way to making this technology a reality and sending it to the moon. So let's dive in. So CADRE's goal is really to do a first-time demonstration of autonomous exploration and distributed measurements using multiple rovers, right? So typically we send single rovers out to either the moon or Mars or wherever we want to go, and they're all by themselves. But what we're trying to do is build teams of robots and leverage the fact that multiple of them can work together to accomplish certain tasks. So they could either explore the surface together, or also in the case of CADRE, we actually have a ground penetrating radar that I'll talk about a little bit later that they can use together to explore what's underneath the ground or the lunar surface. A little bit about our technology demonstration. We are scheduled to launch on April 15th, 2024. So when you're doing your taxes next year, just think about, you can watch CADRE go into space. And then, a few weeks later, we'll actually land on the moon and do our 2 weeks of operations. We're funded by the Space Technology Mission Directorate, STMD, under the Game Changing Development Program. I think it's really worth pointing out, not just because they're sponsors, but we are a demonstration of technology, right? So we're not a science mission. Our mission is to show that the technology works. And for that, we're going to Rainer Gamma, which is this really interesting place on the moon, kind of around the moon's equator, which is known for these lunar swirls, where dark and light regolith mix. And our mission is about 10 Earth days, right? So a lunar day is about 2 weeks long, and we're going to have 10 Earth days to go do our mission. As I mentioned before, CADRE is kind of the next step in a rather lengthy technology development process, where we didn't just start, saying, okay, we're going to go to the moon and go do this exact mission. We actually started many years ago with a different kind of platform called a puffer, a pop-up floating explorer robot. And it was born out of the idea that you really wanted to be able to access different kind of environments on Mars, and it was built to be really, really small and foldable. And it turns out that yes, you can build robots that are that small and that are low in mass and maybe also lower in cost. Okay, I'm getting some messages that I'm still coming through.
Yes,
you are.
Oh, okay,
yes.
Excellent. Sorry. I'm seeing that there are some bandwidth interruptions. So just if anybody has trouble hearing me, just speak up. It's perfectly fine to just let me know. So as I was saying, what we really discovered is that we can build small robots, and then we thought, well, maybe what can we do with multiple of them, right? Now that we can build them small, maybe we can pack more robots onto a mission. And that's how Autonomous Puffer started, which was to investigate how we could use multi-agent autonomy, meaning multiple robots that are autonomously working together, to achieve different kind of objectives like cooperative exploration. And we tested this out on Earth, and it turns out that we were able to do this, and then that prompted us to find an opportunity with the CLIPS program to go and send us to the moon. As I mentioned, Puffer existed out of the need to explore interesting parts of the solar system. So, for example, on Mars, there are certain places that the current rover can't go because it's too large. It can't go underneath these overhangs, and it can also not go up very steep slopes. And then certainly on the moon, we also have some very interesting, surface and subsurface features such as craters. We also have these lunar pits, right? So you can envision that a team of robots goes into a lunar pit and goes and explores the subsurface of the moon in that way. And there's, you really have to design perhaps new systems to go into these places. And again, to re-emphasize, right? It's a lot of this engineering is a process, right? You start off here as we did in 2014, and you build version 0. Version 0 was made out of paper, a couple of motors, some printed gears, and I think some 3D printed wheels, and it was about the size of a couple of quarters. And we were able to show that you can basically shut this robot down into a small business card size and pop up and have it drive around. Then the next iteration actually had a bunch more electronics on it and used the PCB as part of the structure. And in 2015, it got ruggedized so it can survive the Martian environment. And then there was also an offshoot to see what happens when you put it out into the snow. And then we started adding autonomy to it. So in 2019 and 2020, you can see that the platform now has more sensors. It's got stereo cameras on it. It's got some more antennas. It's got an IMU and all these things. So it's an evolution of the platform to support the different needs, starting with just the prototypes, going through some of the environmental things that you need to take care of. And certainly autonomy itself requires a certain level of sensing and compute. So let's take a look at a couple of videos. I think hopefully these are displaying in real time on your screens, but here's a video of one of the paper prototypes being popped up and driving around. Then a few years later, we had working prototypes where they could be folded down. Rather than using your finger, you can actually do this via remote control and a motor, and they can fold underneath this plexiglass platform and also turn around and drive over. So you can see that this platform has quite a bit of versatility. There you go. Puffer goes up over this obstacle as well. And then this is next to one of the buildings at JPL. But we also take it out into the field. So this is a similar Puffer platform with some modified wheels driving up to 60-degree slopes out in the Mojave Desert here in California. And you can see that this platform really does make really good progress on these slopes, but it's not an easy problem. You still have a lot of slip, but it's a very steep environment. But we are going to watch it to the end because it does make it all the way to the top. And then here's some videos of it driving underneath these overhangs. Again, the Mojave was a really great environment for us to go to because it's fairly similar to the kind of things that we were seeing on Mars. And the Earth also has similar environments to the moon that you can take your robots and test them out. So what we typically end up doing, it's at some point we take these robots out to what we call these Earth analogs, and there'll be analogs of some of the destinations that we intend to send our robots. And this provides us also with a lot of valuable field data, including what happens when you drive your robots off of a cliff. Will they survive? And it did fall on its back, but it's able to turn around and keep driving. And here's another video because I think it's just a lot of fun dropping a robot, several meters down and then seeing it drive around. But that's, when we start talking about dropping them into lunar pits, this kind of data is really important, right? Because you can kind of figure out, well, how much of a drop can it survive on Earth, and then you can do the calculations of, well, with 1/6 gravity on the moon, what would that drop be like? So now talking a little bit about how the hardware maps over to autonomy, one of the things that we had to do is we had to equip our robots with a number of sensors, right? Autonomy really means that the robot needs to understand what the world looks like and how it's moving through the world and things of that nature. So we packed it with cameras, radios, motor encoders, certainly the motors to drive the robot, but also to fold the robot. An inertial measurement unit, which is to measure its motion. It's got a computer on it, and it also has some a micro imager to take images of the surface that's on. So you could even probably think of even more sensors to put on this platform for whichever kind of application that you want to use it for. Initially, they were rather small, and then we made them a bit larger because we started looking at the moon, and it turns out on the moon, our robots needed to be larger because we needed to have enough space for a radiator. So they grew a little bit, which also gave us an opportunity to kind of increase the compute power and change out some of the sensors. But here's a picture of the inside of one of our Puffer version 4s, which were kind of the precursors to our card ray rovers, right? We were learning quite a bit of what it takes to put together a robot with all of the autonomy and sensing capabilities to go build a card ray rover. And then here on the right-hand side, you can see that we're working on them during one of our field tests. So at this point, I'm going to hand it over to Federico, who's going to talk to you a little bit more about what we did specifically with autonomy under the autonomous puffer task. So over to you, Federico.
All right. Yeah. So thank you, JP, for the introduction to the hardware platform. Let's talk a bit about what was the original concept of operations for autonomous puffer, and you'll see how this has changed for Cadre. The original concept looked like this: we would land, we would go explore lunar pits. We would land in the vicinity of a lunar pit, about 200 meters away. We would deploy multiple vehicles from the lander and drive to the lunar pit, 100 to 200 meters. Then we would distribute the vehicles around the lunar pit to provide communications to the surface and to prepare for entry. That is number 4. Then we would jump some of the puffers, not all of them, into the lunar pit. We saw that the puffers were light enough that they were designed to survive such a jump, whereas others would stay on the surface to provide relay communications. And then we would go around to explore the interior of the lunar pit. Today, we will focus on the latter part. We won't focus on the driving on the surface. We won't focus on the jumping. We will focus on what do we need? What autonomy do we need? What software do we need to explore the interior of a lunar pit, of a lava tube? But first of all, in the next slide, why do we want to do that? These lunar pits are incredibly interesting from a geological standpoint. They carry geological records of past eruptions. Typically, these lunar pits are generated when a lava tube, which is where lava used to flow, caves in, when the ceiling of the lava tube caves in. So we can see from the stratification of the walls how multiple eruptions occurred. And since this is a sheltered environment, it's it's not subject to the same weathering phenomena as the surface. 2 questions: how do we get in? We talked about that. How do we explore? How do we build the software to get a map of the environment? Well, what we want as an output on the next slide is really a geophysical map. And I think we have a video up top of what this would look like if we did this on Earth. What we really want is a map that tells us this is what the interior looks like, ideally a 3D map that we can navigate so that we can prepare for follow-on exploration. To do that, typically you want to capture a number of images from different standpoints, know where the images were captured, and then pull them together into a 3D model. There is software to do that on the ground. Today we'll focus about what we need on board to do this process. First of all, you need to explore. You need your robots to drive around, to see the environment, thank you, and collect these images. This is called exploration. We started out in 2019. Look at the dates. You'll see how this evolved from 2019 to 2021. Indoors with a single puffer exploring. And you see this happened indoors. This was on a very flat surface, so we're not worrying too much about mobility yet. The rover is localizing itself by looking at the environment and looking for salient features. So you see that we made things easier for it by marking a number of very colorful, very unique features. You see the triangles and the crosses, so the robot would have an easier time seeing where it is. And you can see in the video, this is fully autonomous. The robot is reasoning about the map you see on the right. Black means it's an obstacle, it knows it can't go there. Gray means it's free, it can navigate there. The darker gray it hasn't seen yet. And you see that the robot is driving to places it has not seen yet, so that it covers the entire surface, the entire unexplored area with its sensors. Right now you can see sort of the wedge shape of the sensor as it drives around. So we started out doing this indoors. At this point, we had software that, given that the robot knew where it was, would allow a single robot to drive around and explore. Fast forward, I think 3 years, this was the outcome of the Autonomous Puffer project. The same software running on multiple robots that decided together who goes where. It worked outdoors in a fairly unstructured environment. So the challenge of localizing yourself is a lot harder because you don't have, crosses and triangles. You have a lot of sand, which looks pretty self-similar. And of course, mobility is also harder because now we have real rocks to avoid. And I hope it looks less choppy on your end, but this is a real-time video of the puffers driving around and exploring the mini Mars yard, or now called the Moon yard at JPL. So what went into going from the initial video, indoors, inside the lab, single robot, to this final video, multiple robots exploring outdoors fully autonomously? The only thing we did to collect this was to press run. Broadly speaking, we need four software blocks, and we'll go into some of these. We said that ultimately we want to build a map of the environment. To build a map, we need to know what the world looks like, which we find out from our cameras, and where we are, so that we know where these images were taken. Well, to know where we are, we need onboard state estimation. We need technology to tell us where the robot is. And we don't have GPS on the moon. So we have to reconstruct where we are based on what we see, based perhaps on ranges from other robots. So at least we know I'm a few meters away from that other robot. And based on how many times our wheels have turned, but wheels, of course, slip, and based on inertial measurements. Once we know where we are, we need to decide where to go next. And exploration is the module that does that. Exploration reasons about what have we seen and we know is an obstacle. We don't want to go there again. What have we seen and we know is free, is traversable, and it's kind of boring, but at least you can drive through that. And what are the things we have not seen yet, which are the interesting places where we want to go and observe with our sensors. So this is what exploration looks like. This is the concept of operations, I should say, for exploration. We have multiple puffers, each with its own sensor. It's a camera sensor in this case. We reason about frontiers. A frontier is the boundary between the places we have seen and the places we have not seen yet. And the puffers collectively decide, if you have 3 puffers, they will choose 3 places on the frontier so that they maximize the amount of new things that they see, while staying in communication with each other. We never want them to stray away from communication, because then if there is a failure, we won't know about it, ever. So every puffer is driving around, going to its own frontier, collecting data for that frontier. We want to pull it together. That's why we ensure communications, so that the puffers can then take the local information they found out, send it to a leader, which merges it together into a global map. to do that, we needed to build a mapping database that would allow us to take the individual maps and merge them together. And also, localization is not perfect. And we have, although we'll won't talk about it today, we have a way of revisiting after the fact where the robots thought they were and improving that information based on new data we collected. Oh, you thought you were there, but actually now that I see what the other robots collected, it looks like you were half a meter to the left. This is a complex problem because it requires us to move the data that was collected based on our new estimates of where the paths were. And we built a mapping database, which we call MoonDB, to collect the maps, collect the robot's information, and very efficiently merge it down, store it, and provide a merged version that can be used on board. This is all done autonomously on board. Now, what does this look like when we put it together? Let's see this video. In this video, we're putting it all together. So we have 3 robots. Each robot is estimating where it is based on the camera images that you see. The robot is comparing, I took a picture here, I take another picture a few seconds later. What has changed? That tells me how much I've moved. And they're doing that by tracking the visual features that you see, the green boxes that you see in between images. The robots are also sharing features. Hey, you saw that rock, I also saw that rock. That means that tells us something about where we are. And on top of that, they're also computing ranges between them with radios. They're pinging each other, looking at how long it takes for the radio signal to go back and forth, and using all of this to estimate their positions. On the left, you see what happens. Well, that was very quick. But the point is, if you only use the robot's own localization, you get pretty crummy maps. If you also allow the robot to look at each other and say, oh, I saw the same rock, that improves your map. If you add to that radio ranging between the robots, you get a really high quality maps and you get them on board, which means not only scientists can use them on the ground, but the robots themselves can use them on board to decide where they go next. Next slide. And this is what it looks like when we put it all together. This may be from the same test that we showed before, the at the end, 3 years later kind of thing. On the left, you see the autonomous pathers moving around to explore the mini moonyard. And on the right, I think if we click play on the right as well, we should see the map being filled in. So you see that the robots are driving around. We don't have an overlay, but you will notice that they don't stray too far from each other. This is because they are reasoning about not only what are the most interesting things to see, but also where do we go so that we keep in communications. So when you see a robot exploring the far reaches of that moonyard, you'll see that another robot places itself somewhere so that it has a line of sight to the robot. Of course, radios are much better. We're not giving radios enough credit. We have radios that can go hundreds of meters, but for these experiments, we deliberately didn't tell the robots about how powerful their radios were to get this emerging behavior. So that was a whirlwind tour, but to give you a high-level overview, we started with a single robot exploring indoors, and over 2-3 years, we built it up. We built a state estimation. We built motion planning, which I only briefly talked about. We built an exploration module that works for multiple robots, and we built a mapping DB that allowed us to autonomously explore, to have the technology to autonomously explore under the surface of the moon. And I think now, JP, you're going to tell us about, we built this for space to go from the moonyard to the actual moon.
Yeah, absolutely. So yeah, what Federico just highlighted in this particular slide is all of the technology development that went into making multi-rover exploration possible, and it's really a key capability, right? I think wherever we go in the solar system or even beyond, we'll always want to know what is there, right? What's around the robots or what's around the lander. So this is kind of a key technology, and we really wanted to demonstrate that even if you send multiple robots, they're up for this task. The things that we're doing in addition is going to be these multi-rover distributed measurements, which is basically to say that not do the robots cannot, the robots as a team can certainly explore the surface, but they can also use an instrument to do a measurement where they're in multiple different places at the same time using their instruments and gathering information from that. And specifically in the case of a ground penetrating radar, they're going to be able to basically image what's underneath the surface. So for that, we had to build a new iteration of our robots, and they look something like this. And they have two configurations. They have a stowed configuration, which is when we put them on the lander and that goes on the rocket and it's in flight, they're going to be stowed. And then when they're operating on the lunar surface, they're going to be in their deployed state. And the only real difference is in two cases where, one, you open up the solar panels, right? So we want to have the ability to get energy from the sun and recharge the batteries. And we also want to open up this gray plate right here, which is actually a radiator. And the radiator allows the robots to reject heat because it gets up to 120 Celsius on the surface of the moon and near the equator. So it's incredibly hot, and they need to have a way of basically cooling off. So the radiator is the way to do that. Other than that, they also have dust covers over their cameras, so we pop those open so that the robot can see once it's been deployed. And then it's got kind of everything that you saw before on the puffer, and it's got the computer and batteries on the inside. It's got cameras and all the autonomy sensors. I think what's also unique, though, is to do this distributed measurement. Like I said, there's a ground penetrating radar. So right here on the left-hand side and right-hand side in green, you can see that there is a plate, and that's the antenna. And the antenna faces the ground because when we do the radar measurement, we're radiating into the ground and measuring the reflection that comes back up out of the ground. So here's another look at that. You can see on the right-hand side where I just pointed out the green plate. So you can see that underneath, like half of the robot is this antenna plate. And let's see if there's anything else that's super interesting to point out here. I think we have kind of in the middle along the spine of the robot a lot of our antennas. So we have antennas for communication, but we also have the antennas for the ranging that Federico talked about, that the robots can measure their distances between each other with a radio using time of flight. And then certainly there's also, I think, one more antenna that's used by the ground penetrating radar to synchronize, right? Because what you want to do is you want to make sure that when one robot radiates into the ground, all the other robots are listening, and then they actually take turns doing the transmission and receiving of the radar signal. So let's talk about the ground penetrating radar a little bit more. I think it's a really interesting piece of technology that we're demonstrating that's also really completely new. Today's state of the art, so if you looked at what exists today in space, you have a couple of rovers, including the most recent Mars rover, and they have a ground penetrating radar on them. But they only have a single ground penetrating radar, right? Because they're robots, they're rovers that are going to Mars or to the moon all by themselves. So the best thing that they can do is they can drive along some path on the Martian or lunar surface, and they can radiate into the ground and listen to their own radar reflection. And that means that you only get a 2D slice of what's in the ground, right? So you get this 2D view, kind of like an ultrasound of what's in the ground. Where Cadre is really advancing the state of the art is that by sending multiple robots, we do something called a multi-static ground penetrating radar activity, which is all the way on the right, which is not just doing multiple parallel monostatic measurements, but what we're doing is we're driving the robots and having them radiate and listen to their own signal, but also listen to the signal from all the other robots. And when you do that, you get a very distinct advantage, which is that you can go from these two-dimensional slices of what's underneath the surface to three-dimensional. And in fact, you can even do better than just doing multiple monostatic. By really having these robots work together, you can get a clear picture of what's in the ground without a whole lot of noise. And that's really a new way to do science measurements, and certainly ground penetrating radars are not the only ways that you can do it. If you think about the way that seismic networks work on Earth, we have multiple different stations throughout the country that are listening to seismic events, and that helps us pinpoint not just the magnitude of an earthquake, but also kind of the direction and other properties that you wouldn't be able to do if you only had a single listening station. And I'm sure there's other applications out there that really do leverage the fact that you want to have instruments or sensors on different robots that are listening at the same time. So Cadre's technology really does enable this distributed measurement. Specifically, our robots work together, so they're doing this transmitting and receiving together, but they're not just doing that in arbitrary locations. They actually work together to be in a specific formation, right? So if they have a certain spacing, that actually translates to being able to image to a certain depth into the ground. So you can imagine that maybe for one of these drives, they're all going to be 2 meters apart, and then they're going to do another drive, and they're going to be 4 meters apart. But basically, by them working together, they can go and image the subsurface in any of the ways that the scientists want us to do. It's also important that they're autonomous. One of the reasons for that is that when you're out in space, you have communication delays, but also if you just think of it as purely from a perspective of scalability, if you want to start sending out 3, 4, 10, 50 robots, it's going to be very difficult for 50 people to coordinate on the ground what 50 individual robots are going to do and make them work as a team. It's much better to give the robots the ability to figure out amongst themselves what to do and to execute what you want them to do as a team. I think distributed in our case is fairly obvious in the sense that what we've done is we have transmitters and receivers on different platforms, right? That's something that you can't really do with a single robot, but that you can do with a multi-robot system. And then finally, we already spent quite a bit of talking about exploration, right? I mean, exploration is important for being able to do your planning. So if you want to do a survey, you want to know what the surface looks like so that you can plan around obstacles, because you don't want to drive your radar and your robots into a rock. But at the same time, what you're also doing is you're getting contextual information about the surface of the moon, and you can correlate that to things that you see in the ground, right? If you see, for example, some dense rocks underneath the lunar surface, and you have the information from the surface that there's a crater, then maybe that's ejecta from some sort of asteroid that might have hit the moon a long time ago. So being able to both understand what's on the surface and underneath the surface gives you a much better idea of what's going on than just having one or the other. So just to kind of reiterate the kind of the key technologies that we're building, there is the relative position determination. So understanding where the robots are relative to each other is really key for them to be able to plan out what they're going to do together. And then certainly they have to go and plan, not just for themselves, but for the team has to come up with a solution that makes sense, right? We can't just go in all different directions and expect that the ground penetrating radar is going to work. We actually have to be in this physical formation, and we have to modify the formation to avoid obstacles and to follow the path that the scientists want us to follow. And then we also have to record all that information and make it both available to the robots to be able to use it for future decisions, but also on the ground, we want those maps, right? We want to look at what they found on the surface and underneath the surface of the moon. So it's really important that you manage all this data that they're collecting and get that back to the ground so that we can process it. And I think at this point, I'm going to hand it back to Federico, who's going to tell you a little bit more about kind of the cadre version of all of these autonomy technologies and how we've implemented it for our particular technology demonstration that we're flying next year.
Of course. Thanks, JP. Yeah, so at high level, this is what our autonomy architecture looks like. At the top, in the ground, there are always humans in the loop, and the humans in this case are providing high-level goals to the system. Go explore this region, or do a GPR survey along this path while staying in this formation, in orange. Then in green, on board the leader, we have a leader among the agents that is elected, And on this leader, first of all, we reason about onboard resources. How much power do we have left? What is our temperature? To decide when the agents can wake up and operate and when they should sleep to cool down and recharge their batteries. Once we figured it out, when the agents are available, we have a second layer also on the leader, which is the team planner. And the team planner decides who goes where. For exploration, it decides which agent goes to which frontier. For formation sensing, it tells the agents where each of them should drive so that they stay in formation. Once we've decided this, we pass the ball to every agent. Every agent has an agent planner. And the agent planner is the one actually executing the commands from the leader. For exploration, the team planner tells the agents, well, here's a region for you to explore. The agent is the one deciding which specific frontier to go into that region. I misspoke earlier when I said the team decides that. For formation driving, we'll talk about that in a moment. The team planner tells the agent, stay in this tube at roughly these times. The agent is the one responsible for actually doing the driving. And the responsibility is shared between the execution engine on the agent and guidance, navigation, and control, which is the one actually building maps and looking at obstacles and planning a path around these obstacles. We said that there is a leader. We'll talk about that in a moment, but we don't have a fixed leader. We elect a leader so that if one of the agents dies and that agent is the leader, we're not lost. We can elect a new leader and continue operating. And there's a leader election module that does that. Now, on the next slide, broadly speaking, any autonomy stack looks a bit like this. On the left or at the top, you have ground operators that provide high-level goals. In the middle, you have planning, scheduling, and execution that decides, reasons about resources and makes high-level decisions. When do we sleep? When do we drive? Where do we go? And then all closer to the hardware, all the way to the right, we have guidance, navigation, and control, which actually worries about the interaction with the physics of the environment. Where are the obstacles? Can I traverse this piece of ground or not? Should I steer right or left? What should my wheel speeds be? I'll talk about the centerpiece, planning, scheduling, and execution, which in my mind is really the, what makes an autonomous robot different from an automated one. And when you build a planning, scheduling, execution architecture, there are, broadly speaking, 6 questions that you want to address. How do we coordinate? How do we make decisions together? If there is a leader, who is the leader? Where are the decisions made? And then on the algorithmic side, how do we manage our resources? When do you drive and when do you sleep? How do you explore? And then you perform a descriptive measurement. So let's talk about how we coordinate and how we choose a leader. There are, broadly speaking, 4 ways of performing, of making decisions in a team of multiple robots. The simplest one is you pick a leader. Like you decide this agent is the leader, it's a monarch, and that's it. All information goes through that leader. And this is the simplest architecture you can build, because the way it works is all agents tell the leader, this is my state, this is my temperature, this is my power. The leader makes a decision for everyone. You do that, you do that, you do that, and distributes that. So why don't we always do that? If this is the simplest thing to do, sometimes leaders are deposed. Sometimes monarchs are exiled to St. Helena. Sometimes you lose the leader. Either because it's physically lost or because it's out of communications. When that happens, a monarch architecture is dead in the water. You can no longer communicate with the leader. The agents are just waiting to hear back. Not great. So the upgrade you can do to this is to have an elected leader in the next slide. The architecture looks the same as before with one extra step. You have a mechanism by which the agents together decide on which of them should be the leader. The advantage of this is if for any reason the leader is lost, we are able to pick a new one and we are not dead in the water. The disadvantage of this is that leader election is not an easy problem, because you have to not only pick a leader, but make sure that everybody agrees on which agent is the leader to avoid partitions in the network. So you're putting a lot of complexity into that box on the left. But if you're able to do that right, you get the best of the leader architecture without a single point of failure. There are 3 more things that are done in the literature. One that is used a lot in highly resilient applications is implicit coordination. So this one is tricky. The way it works is that every agent pretends to be the leader. All agents communicate all relevant information with everybody else. So every agent has the information to be the leader. Then every agent thinks, well, if I was king or if I was the monarch, what would I do? And they come up with a plan for the entire system. And then, without checking what the other agents decided, every agent executes its own part of the plan. Oh, if I was the monarch, this is what I would have everybody do. In particular, this is what I would do as part of that. Let me do that. And if all the agents have the same information as inputs, and if all agents are making decisions in the same way, if they're using deterministic algorithms, this will result in implicit coordination. The risk of this is, of course, if agents have different information, they may make subtly different decisions. You get things like two agents doing the same thing because they both told, if I was the monarch, that's what I would do. Or nobody doing something because one agent told another one to do it and vice versa. The upside of this, however, is you're never waiting to hear from the leader because you are the leader of yourself. So if you are in a scenario in which, agents are added to the system and lost very quickly, this makes sure that you're never lost in the water, which is, dead in the water or lost, which is great for highly resilient architectures. There's another approach that you may have heard about. This is called auctions on the next slide. Explicit coordination or auctions. In this approach, the agents explicitly trade tasks. One agent decides, oh, this thing needs doing, and asks everybody else, who wants to do it? And the other agents, the other robots can bid on it. Oh, I really like that. Or, well, let me suit it for it, but I'm really far, so if you can give it to somebody else, that would be great. This has been widely used in the academic literature, not so much in the field, because you need somebody to run, the explicit coordination. You need somebody to run these auctions. So it starts looking like leader election with extra steps. And the final approach, which I'm sure you've heard about because it's been very popular in the robotics community, is emerging behaviors or swarms. Here, the idea is that every agent has a very simple local behavior. Things like, I'm going to look at my 3 nearest neighbor and do the average of what they're doing. And you design this local behavior. I'll do the average of what they're doing so that in aggregate, it results in what you want. For example, what I just described, in aggregate, look at the average of your neighbors will result in all agents going in the same direction. These are the 5 ways you can coordinate multiple agents. And there is no right or wrong answer, but for Cadre specifically, we cared a lot about resiliency. We cared a lot about consistency of decisions, but we were not worried about agents appearing and disappearing. So the elected leader architecture, in which we decide who the leader should be, and if that leader disappears, we just nominate another one. But all the coordination decisions are made on the leader appear to be the right one for our approach. I only have a few minutes and I want to leave time for Q&A. So this is a whirlwind tour. We have a longer version of this talk. You can ask us for it. I think we recorded it. Let's move forward to as far as you want to go, JP. Sounds good. So let's talk about, we made these decisions. We want to talk about how resources are managed. Let's talk about how we do the GPR survey. What do we need to do a GPR survey? We need the robots to drive information with each other. GPR scientists tell us the robots have to be at this distance from each other. Robot 1 and Robot 2 have to be at this distance. Robot 1 and 3 have to be at this distance. 2 and 3 have to be at this distance, which gives us a fixed formation. We can deviate a little from this formation, but not too much. And we are told, if you have a rock and you have to drive around it, you can move around by maybe 10 centimeters, but not more. And as a whole, the formation of the agents has to drive some path because that's the area that we are interested in. So how do we do that? In the next slide. This is the most technical slide that we have. We use a sampling-based motion planner. We have three steps. We use a sampling-based motion planner to come up with a trajectory for the entire formation. If you don't know what a sampling-based motion planner is, don't worry about it. Sampling-based motion planner gives you a trajectory that is collision-free, but can be a bit jagged. So then we smooth it to make sure that we don't keep driving left and right because the algorithm wasn't smart enough to do that. And then we put timestamps on this trajectory, and we give every robot its own piece on the trajectory. We tell every robot, go to this place at this time, this place at this time, this place at this time. And if they do that, there will be information, even though they're not talking to each other. On the right, you see a test that we ran on this. This was indoors, but with robots whose mobility stack, whose wheels and motors reproduce pretty closely what we'll have on Cadre. And you can't quite tell, but they're driving uphill. This is hard to drive. And they're doing great. Slipping a bit, but even though they're slipping, they're able to maintain the formation. And when this video is over, I think I'm turning it back to JP for the last 3 slides.
Yep. And they do make it. I might urge them to go a little bit quicker than they are in the video. There you go. Yeah, so that was quite a bit of content to get through to tell you about all the technologies, but I think it's kind of a natural thing that when you try to build up a team of autonomous robots, there's quite a bit of technology to make that all work together. But we've built, we've shown you how we've prototyped and tested and built a lot of the components or technology and implementations that are going to go into Cadre's technology demonstration. We're going to be able to have them work together as a team, know where they are, take the measurements, collect all that data, and send it back to Earth so that we can look at these awesome subsurface images of the moon. It also shouldn't be surprising that it takes a team to build a robot team. So there's a large number of JPLers that are working on this. Here we have the multi-agent planning and execution team that Federico leads, as well as the motion planning or the GNC team that we highlighted some of their work as well. And then what you're not seeing is the rest of the team, which is working on avionics, flight software, mobility, systems engineering, project management. There's so many different areas of expertise that it takes to put a project like this together and to make it be successful and go to the moon. So everybody that's on the team has a different area of expertise that they're bringing, and that's really what makes us successful. Is that it can't just be done by by Federico and me. It really takes a number of people to make that happen. So I think at this point I want to open it up to Q&A. I'm going to play just a video in the background, yeah. Thank you.
All right, so we're going to go ahead and run this like we did for mission 1 and also for the meet and greet. So if you have a question, you can raise your hand, go ahead and type your question in. When we call your name, we'll have you click submit, and then we'll have them answer. We don't have a lot of time left, so I'm not going to guarantee we will not get through all the questions. I will guarantee that, but we will get through as many as we can here. So let's go ahead and have Jaden, if you want to go ahead and submit your question. Says, how do you plan around materials? How do you plan around materials for the rover to keep a light mass, but also work around the extreme temperatures?
That's a really good question, and unfortunately, I'm not a mechanical or materials person to answer that with any sort of technical depth. But the good news is that I think we have office hours for a hardware person that can answer that. But in general, what I do know is that we have a team of mechanical engineers that are assigned to go build the chassis, and they spend quite a bit of time modeling places where you can optimize for removing mass, and that was really important. And not just on the rovers, but also on other parts of the system. For example, where the rover attaches to the lander, we've had to go in and for example, take off the sides of the initial box that we had to save mass. So yeah, it just takes a good bit of understanding of creativity in terms of coming up with ideas of where to save mass, but also then having to go and do the analysis to make sure that you're not like structurally doing things. And I know that the team has looked at also various different processes of whether should we just take aluminum and water jet it, or should this be 3D printed? So those kind of things have been done by the team. So I can't give you like an exact answer of what equation I would use, but I know that's the kind of processes that the mechanical teams follow to come up with the design in the end.
Awesome, thank you. Edwin, if you'll go ahead and post your question. And while he's posting this, I'm going to say this: all of our position-specific advisors are all members of this same team. So you're going to get some really good information from them, like they were just stating. So Edwin, if you want to go ahead and post yours, I'm also going to ask Isaac to go ahead and post yours at the same time. All right, so Edwin's question: have you experimented with different forms of locomotion like tracks, legs, etc. for Cadre before the final design selection?
So for Cadre, we did not experiment with those other mobility mechanisms. A lot of that kind of experimentation happened way before Cadre. I would say through a variety of different research projects. So we have legged motion platforms and ones with tracks and ones with wheels. You saw that even the original puffer was two-wheeled, but then we did some analysis for the lunar terrain and figure out that a four-wheeled robot with a fixed suspension was the best thing. I think the one thing that we did experiment with at the very beginning was whether we wanted to have an active or active/passive suspension, but we ended up just having a fixed suspension for the robot. But yeah, it's a great question because it's a really good thing to think about, and it just turns out that four wheels was the best design for our particular project. But I can envision that maybe if you wanted to go into a different lunar environment, or you were going for a different planetary body, that some of the mobility systems that you suggested would be more appropriate there. So yeah, great question.
All right. E. Gomez, would you please go ahead and post yours? So Isaac's question, it says, for software specialists, what do you recommend we work on for this mission specifically, since there has been so much already done, like on a power management system code, autonomy code, etc. That might be something that's better for the job specific advisors, but I'll let you answer it if you feel it's something we need to answer now.
I think all I would say is that really the way that you figure out what software you need to build is through thinking what are your, you're going to figure out what your mission is, and from that you're going to have requirements, right? You're going to have a task that you want the robots to do, like exploration or distributed measurement or whatever else it may be. And from that you can derive what kind of capabilities the robots need, and that then your software is basically implementation of that. I think you kind of saw that our architectures between autonomous puffer and Cadre were actually different, and that's because they had to fulfill different tasks. So think of the software that we've developed so far, both JPL and other NASA centers or in industry. Think of those as the building blocks, and then you're going to have a certain set of building blocks that are available to you, some building blocks that you're going to have to build yourself in software, and then it's your job to also put them together into an architecture that does what you want them to do. But yes, I think that's a great question for office hours as well, because I think that you could have a longer discussion on that as well.
Awesome. All right, so this is going to be our last question here, guys and ladies. So again, if you can bring your other questions to the office hours, that would be great. It says, how long is Cadre's entire line of code, and what programming language is it being written on, and why?
I don't think we've measured how many lines of code we have, but what we are currently using is C++, specifically the C++ 14 standard, and we are using a middleware called F', which is open source and was built by JPL. Other alternatives to that are in the research world, we typically tend to use something like ROS. So if you're familiar with ROS, you may also find that you see a lot of similarities to F prime. And I know that also there's something called core flight software. So CFS is another option for you to look at if you're interested in the middlewares that allow you to kind of build up such a system. But they tend to all be either C++ or C, and I know that ROS also supports Python.
All right, thank you. So we are at the end of our time today. I just want to say a big thank you to Jean-Pierre and Federico for coming in and talking with you. You're going to hear this a lot, drinking from a fire hose, and you just got doused with it on that one. A ton of information, but it was awesome. Thank you so much. Sarah Beth, would you like to close us out? Before you do that real quick, I apologize. Remember, 1:30 Central Time, it will be the start of the office hours. They will run for 1 hour. And then we have debriefs starting at 3 p.m. and all of those links are in the Canvas calendar. So with that, Sarah Beth, I'm going to turn it over to you to close us out, please.
Thank you, Mike. And thank you so much, Jean-Pierre and Federico, for the awesome presentations today. I know it's going to be so useful for the students, and I'm sure you guys are going to get a lot more questions later today at the office hours. But just thank you so much. I hope you all enjoyed orientation today. Please let us know if you have any questions, and I'm looking forward to seeing how the rest of your day one goes. So have a great rest of your day, everyone, and good luck.
Thank you.
Bye.
Bye.
Have fun. Hey, take this as having fun. Have fun with this, and this will be a great week for you. So reach out to us if you have any questions, please. Whoever's recording, if we can go ahead and shut the recording off.